So, hopefully the music is low enough and the audio, the microphone is loud enough that you can just stick up the overall volume. Much better. Good. So, hello. I hope it's been a good week for you. I can't believe it's been a whole week, let's be honest. Yeah, time moves in a very unusual way at the moment. So I hope you're all good. Today I have got a good class for you. Last week's I think was a little bit on the long side, but this time it should be good. So if I bring it up to here, today is all about mutations, how we are all mutants. Yes, you included. You don't have to be a teenage ninja turtle to be a mutant. And how basically mutation is the engine behind evolution. So personally, I am not a geneticist. I find the inner details of genetics quite dull, if I'm honest with you. Some people find it absolutely fascinating how simple chemistry can dictate life. Personally, I prefer the bigger whole organism stuff, but you need to have some idea of evolution, you need to have some idea of genetics. This is what happens when you've been working from home for a while and I've got literally 6 things to monitor at the exact same time that I am talking. I had a little rant on Twitter the other day about all of these TV chat show hosts doing terrible jobs of their programs online when they're edited and they have access to a huge crew. So, we're going to be doing mutations and a little tiny bit of genetics, just enough genetics that you can kind of find out what you need to study evolution. So I'm going to try and have this entire lesson over by 5, partly because the clocks have now changed. It is a Thursday, if you did not know. It is 4 o'clock UTC +1. For those of you for whom time has become an even more abstract concept than it already was. So if I finish this early, I can go out for a walk in the countryside afterwards. So that would be nice. So let's start with this. We are written in DNA code. How am I going to start this? So I'm assuming for the purpose of this video that you have virtually no background knowledge about DNA and evolution, and then as the weeks go on they will build up on each other so that later streams will be more complex than earlier streams. But for now we hear this thing called DNA, we hear genes, we have mutation, we have variation, diversity, selection, all of these words. Oh my god, biologists love their technical words. Got alleles, got codons, amino acids, bases, all of these things. Basically just trying to make it more complicated than it needs to be. I am going to switch over. So last time I know you mentioned that there were some weird buzzing noises coming from my graphics tablet. It's not even my graphics tablet. A friend lent it to me a few years ago and I've never given it back to him. Thanks, John Mark. So I'll try and unplug it whenever it's not in use because I haven't worked out what's going on with the cables and why it makes a very faint buzzing noise. But if you do hear a faint buzzing noise, please know that is me and not your ears going funny and a new symptom of the C word. So with that, so we are written in DNA code. We can take it to the notebook. One of these days this will feel normal. So there we go. Actually, I don't want to do that. I want to say that then instructions to build us are written in DNA. So I briefly touched on this analogy before last time, and if I move my sugary mint tea, because I've got a bit of a sore throat because I've not been practicing talking for the last week, it's resting on this, which happens to be one of my recipe books, which is Good Food. One of the just any old BBC recipe book. It's got nice pictures in it, so that's why I like it. But if, for example, we wanted to make, I don't know, do they have any desserts in here? Oh, they do. If we wanted to make a fruity summer charlotte, which is basically it's a fancy bread and butter pudding. So it tells you what it is that you want to make, a fruity summery charlotte, a buttery biscuit base, a fruity summery charlotte, and then it gives you ingredients and it has a recipe. And this is written in English. So you can see that there are Latin letters, or you could if I wasn't using a fancy camera that has a very shallow depth of field, but it's written in English letters. And I say this, and it sounds super basic when I say it, but it's because when we go through this, there'll be more and more jargon and there'll be more and more words, but at its most basic, imagine that you, a person, are a fruity summery charlotte, and there are lots of ingredients to make you a person. You need hair, so that's a protein, that's collagen. You get collagen in your skin as well. There's protein, keratin in your fingernails. In your blood, you've probably heard of hemoglobin. That's an ingredient to make a fruity summery charlotte, or in this case, a grey spring Sally. And then you've got the ingredients which tell you how to make the thing, how to put it all together. DNA is a chemical. And unlike what the press would like you to believe, the word chemical doesn't mean bad. Chemical just means it's made of stuff. Like everything is made of chemical. Air has chemicals in it. DNA is a fancy chemical, deoxyribonucleic acid, that you will have seen in the media looking something like this. This is DNA for deoxyribonucleic acid. So it's just a chemical. It's in the same way that cooking salt is sodium chloride, or in the same way that water is H2O. It's just a chemical. What's interesting about this chemical, though, is that it's more like a group of chemicals that are very, very similar to each other. So what these little strungs are the letters in which everything is coded. And so I could also write out this string as, if I was to, so imagine it's a ladder that normally is all twisted up. So it's got rungs and two long, what we call the backbone. If you untwist the ladder, each rung can be a different letter, like the letters in our alphabet. So this one might say, so you can imagine reading DNA, and you're literally reading it. It has a direction to it. And as you go along, you're like, oh, this DNA is the gene for preheat your oven to fan 180. And so people are saying hair is keratin. You're right, hair is keratin. Collagen and keratin are both structural proteins. I'm sure there is collagen in hair as well as keratin, but it is, you're right, mostly keratin. So DNA is literally a written instruction, but obviously it's not written in English. It'd be nice if it was. It's not. And oddly, their alphabet only has 4 letters. So instead of having A to Z, so that's English. DNA language has A, T, C, and G. And that's it. Everything that you know of is written in those 4 letters. Sometimes you get a 5th one thrown in when it's a slight variant of DNA, but we're not going to go into RNA today. RNA is boring. We're going to ignore it. And so if you're wondering what these letters are, I remember in school being like, but what are these? Like, there's no letter A written in my cells anywhere. Like, what is it? It's actually just another chemical. So A is adenine. Like, you don't need to know these names, but for me, I found it really helpful knowing what these were. Guanine. So they are themselves just these weird chemical blocks. These are not accurate depictions. And then depending on how you string them up, you get your DNA. Someone with a degree in RNA biology is objecting to me saying that RNA is insignificant. So yeah, these are just chemicals. But once you've got these 4 letters, you can create stretches of DNA called genes. So we've got DNA is almost like the language. This is where I find out that my analogy is probably going to break down. We've got genes are the recipe. So you might want, and when we're talking about a recipe, the thing we're cooking up with genes is always proteins. If you want to make something that isn't a protein, you've got to make a protein that will make it. So say you want to make a special type of sugar, you've got to make a protein that will make that sugar. If you want to make a special type of fat, you've got to make a protein that will make that fat. And by and large, everything revolves around proteins. Proteins, again, like you're thinking of protein like chicken, like meat, like eggs. It's just another group of chemicals. So in the same way that fats, you get olive oil, you get butter, you get cheese. What other fats are there? Lard. They're just groups of chemicals, and proteins are good chemicals because they've got really interesting structures. So it's like you have different tools in your kitchen. I don't know why I'm labouring this kitchen analogy, but you can make a spatula or a knife or whatever. Proteins are just darn useful molecules. So we've got genes, which are the recipe. And I mean, genes also code for proteins, but they can also control OR switches. So what do I mean by OR switches? Because you not only have these things that, sorry, trying to read comments at the same time as doing this. So you've not only got the genes to say, make a blue protein here, or a brown protein, I'm trying to work out where my eye is, or a brown protein here. Actually, there isn't a blue protein. Make a brown protein or don't make a brown protein, or make straight hair rather than curly hair. You also need things to say, actually, don't make brown here, make it in here. Don't grow hair here, grow hair here. So it's like telling you when to do it, telling you when things need to be switched off. So why is the shape of proteins so important? Because the way that proteins work is to have a very special shape. It's like, why is the shape of scissors important? Because if my scissors are completely wobbly and they don't come together nicely, it can't do its job. The way proteins do their job is to be of a very specific shape, in the same way that, what else works on shape? So we often think of like a lock and a key, outdated idea, but if you don't have the exact shape of lock, then your key's not going to work, it's not going to open. So enzymes are types of proteins. So again, when you hear about enzymes have a very specific function, enzymes is a huge group of proteins. You also get structural proteins, things like that. And you have DNA, genes, and the way that you go from DNA to proteins is this tells you which amino acids to use. And I told you there's a lot of terminology in genetics. That's why I don't find it that interesting. But a protein is just a string of amino acids. So think of this as the letters in the language. This is the letters, this is the language, and these are the words. So, is that how I want to do it? Kind of. So we have, and I have no idea if this is going to work or not, but you can tell it's getting to a good bit. Actually, no, I don't want to put this on just yet. So remember, before we get to what I think is going to be very exciting, in DNA we have the letters A, T, C, and G, and then 3 of them together tell you which amino acid to use. So if you've got, let me quickly, got like, I don't know, CAT, that tells that in the code, like you're not supposed to be able to work it out from behind, but that tells you that you need to make a histidine, which is a building block, histidine. Or say you wanted GGA, that might give you glycine. So that's how it works. Now, with that knowledge, where do I need to go to? I need to go to here. We can play a game of genetic bingo! Now, I have no idea how much this is working. Hopefully, I can't actually hear it, but hopefully you have some very cheesy background music going on here. So this is where I want you all to play along at home. And hopefully with this, it'll give you some of an idea of how all of this works. So firstly, don't be confused by what's on the screen. We're going to ignore that for now. The first thing you need to do is think of a 5-letter word, but it mustn't use the letters J for January. I don't know my police alphabet. O for orange. I don't know what these are. U for umbrella, or X for X-ray. So please, can you, in the chat, write a 5-letter word. And there we go. So Juliet, or Omega, Orange, Oscar, Someone's pulling through. Juliet Oscar Uniform X-ray. There we go. So you can use any of the English letters other than those 4. So you can use A, B, C, D, E, F, G, H, I, K, L, N, N, P, Q, R, S, T, V, W, Y, and Z. You can use any of those letters. Write a 5-letter word in the chat. I promise I'm not going to look at your words for now. But this is just so that you can remember it. And that word is your bingo score. I'd never played bingo before until at the YouTube space. Had a great game. They put it on one night. Where these 2 guys about my age are dressed up as grannies, pretending to be from America with terrible accents, played a load of hip hop while we played bingo. It was actually quite tense. You got to work fast on bingo. And so, okay, so you've got a 5-letter word. Now, that is the protein. That word is the protein that we're going to make with the gene. And I'm going to call out the letters, the amino acids that you need to make to build your protein. So your protein consists of 5 amino acids. Those are letters. And actually, in biology, we give each of the 22 amino acids a letter. And as you can see on the screen, we have top left, we have F, which is phenylalanine. We've got leucine. Ones you might have heard of, glutamic acid, so glutamate, that's given the letter E for some reason. Tryptophan, which is what makes you sleepy after you've had a big meal, that's given the letter W. So you've got your amino acid is made, your protein is made of 5 amino acids. Your word is made of 5 letters. Now I am going to, as the caller, call out the DNA code. So what you're going to have to do is you are going to have to translate from the DNA code, which remember is only written in the letters A, T, C, and G, into your amino acids, which are the 22 letters, so the alphabet excluding J, O, U, and X. And then when you get it, you can tick it off, and first one to get all 5 of their letters can shout bingo in the chat, and you will win the prize of satisfaction. I don't know, we'll work something out. I might send you a video or something. So how do you read this chart? So, like I said, it takes 3 DNA letters to code for 1 amino acid. So I'm going to call out, for example, we've said that cat is histidine. So C-A-T. C, you start off on the left-hand column, and where it says first base, you read down, you go TC. Okay, so you can see that, so basically you can search the entire table for the letters CAT, but it's organised in a nice, easy way for you. So all the ones that begin with C are on that second major row. And then all the ones that have A as their second letter, if you go down from A at the top and follow it down, and then you'll see all the ones that have T as their last letter. So you can see how you can read, you can just search the entire table, but I'll give you a moment now to have a quick workout of what's going on. And you'll notice that some have more than one code. So for example, leucine has six different codes. So if I was to shout out TTA, TTG, CTT, CTC, CTA, or CTG, all of them would give you the amino acid leucine, and you can tick off L on your sheet. If you don't shout bingo now, because I've not even started yet, honestly, you're banned from fair play. So if you hear a letter and your word has got that letter more than once, you have to wait until you've heard it twice. So only tick off one letter at a time. And here we go. Now it is time for genetic bingo. And I am going to make a list of which ones I have done. So starting off, we're going to go with GAA. For those in the know, it's glutamic acid. So if you have glutamic acid, if you have the letter E in your word, you can cross off it once. If you've got more than one E, just cross out one of them for now. And the next amino acid, or the next codon, is TAT, or tyrosine. And the next one is ATA, isoleucine. We've got glutamine in the house with a CAA. That's CAA for glutamine. I could totally be a bingo caller. We have TTT, all the T's, TTT, phenylalanine. We have GCA, GCA, alanine. And we have call to action, CTA, leucine. We have TCA, TCA, that's serine. Sorry, those of you that are saying that you can't find B, you're right. Which one is it? There should be. I think aspartame can also be B. If you've got a B, feel free to change it because there isn't one on this table. I'm fairly certain there is an amino acid with B, but I used to know all these off by heart. This is the thing. For my university, I had to memorize what all of the letters went with what. So for example, remember that M was methionine or whatever. Talking of that, let's do AAA. It's a tiny battery. It's lysine. Give me a C, give me a G, give me another C, and we've got arginine. There we go, B is asparagine or aspartic acid, that's what I thought, so it has multiple, some of them have multiple options. And we've got I'm trying to look through and see which ones we've already got. We've got TTA, Tata, leucine. We've got the friendly pussycat, CAT, histidine. GAG, glutamic acid. GTA, I think that's a famous video game that I don't know. Grand Theft Auto, Valine. We have ACT, better act now. It's threonine. We have a bingo! Sandcastle, what was your word? We have a bingo. Sandcastle has a bingo, Starch has a bingo, Island has a bingo, Chimigza has a bingo, Sandcastle has river. Do we have river on here? We have R-I-V-E. I mean, technically we've only had one R, but let's be honest, we played this long enough. That was our game of evolution bingo. Genetic bingo, there we go. Enter, do we have E? I don't think we had an N yet. Anyway, so now I hope you can realise that that DNA is just a code, and you can look at the code, and with that code you can work out what the protein is going to be at the end of it, what the word is going to be. What am I doing? I don't know, Fercho Vega. What am I doing with my life? I'm playing genetic bingo to teach genetic codes. So now we know that. Next, okay, we've got half an hour to do the rest of it, guys. That was by far the most fun bit. We're going to rattle through the rest. DNA, when DNA is copied, you get mistakes. So when, like, imagine you're writing out all the words of Shakespeare by hand. Someone hands you their copy, you write it out, and oh no, you spelt achieve with the I and the E the wrong way round, because frankly, I always make that mistake. Or you copied it over and you wrote dog instead of God. Like, when you're copying things, you're going to make mistakes. But then when you hand your copy onto the next person for them to copy it, that is going to continue down the line, and that's what we call a mutation. Because if we think of DNA as literally just this language that words are written in, mutations are just spelling mistakes. And they happen all the time. They happen... Oh, let me go back to the notebook. Oh, I feel like such a teacher. Number 2. DNA mistakes happen, and they are called mutations. Oops. It's all right, because if I get anything wrong in this bit, I can say it's deliberate and it's just a mutation of the fact. Things to know about DNA mutations. They're spontaneous. Why the exam board wants you to know that, I don't know, but I did do a little bit of research as to what the exam board wants you to know if you are studying in the UK. So it's not like someone goes around deliberately causing mutations. They just happen, you know? Mistakes happen. It just does. But there are some things that can make them happen more than others. And so you've probably heard about mutations causing cancer. Well, guess what? UV radiation, or in fact, any what we call ionizing radiation, ionizing radiation, certain chemicals, these all cause mutations, and so we call them mutagens. Mutagens just means something that causes mutations. Like I said, there's got to be a fancy word for literally everything in genetics. It gets a little bit overkill. Mutagen, something that generates mutations. I know, I didn't come up with this language. Now we've got a good bit here. Oh, what is unionizing or unionizing? Depends on how you read it. So we've got 3 types of mutation. And what was the winning word we had again? We had river, wasn't it? So that was our winning bingo word. So this is our protein. That's gone off. There we go. And remember that the DNA is written in 3s. So quickly looking at my list, R was arginine. I remember that one. So that could be CTG, arginine, or CGA. I could be ATA. V could be GTA. E could be GAA. So that's what our DNA code is. And now you've played bingo, you're not scared by this really long string of 4 letters. You know that just, if you split it up into 3s, that just spells out river, which is our protein. So now there are 3 types of mutation. I'm going to take just the first few things for this. C, T, G, A, T, A. We've got number 1, insertion. No sniggering at the back, please. With insertion, what happens is it's going along, copying it. How am I going to do this? Oh yeah. So it's going along, copying it. It's thinking, oops. It's going C, T, G. Oh look, what's that over there? There's a squirrel. And it loses focus, and then it carries on writing the code. And so it's like, oh, there's a new letter in here. There wasn't that letter in there before. What used to be a 6-letter code is now a 7-letter code. So that's insertion. We've got deletion, which is where you might go C, T, G. Oh look, isn't that a lovely bird? In my head, DNA is a highly distracted by wildlife person, much like me, and it continues on doing it, but you'll notice that it's missed out a thing here. So what used to be a 6-letter word is now a 5-letter word. And then finally, we have the footballer's favourite, substitution. which is where you're going. I've got to remember actually what the original one was. That's the original. So you're going C, T. Now, I can't quite read that handwriting. Is it a C or is it a G? You know what? I think that handwriting says it's a C. Oh, that should have been in a different colour, shouldn't it? I'm going to say that's a C because the handwriting wasn't very clear. A, T, A. So those are your 3 types of mutation. And yeah, some of you noticed that actually it now, this one spells out a different word, because if we're reading it in 3s, this is no longer our 3, but this is our 3. So that completely screws up the entire word. So if we have, going back to our river example, maybe it will mutate to riser in one mutation. Maybe a different mutation might be rider. And these are all mutations on the same gene, so we call these alleles. They are variations on a gene. Oh, what a great pun! I just thought of it on the spot. Oh, look at that! Variations on a gene, like variations on a theme. Oh, that's gonna keep me going for the rest of the week, that pun. Okay, so that's that. Let's go back to the main. Oops. Here we go. So we know that when DNA is copied, we get mistakes. Mutation does not mean bad. So this is really important. In media, when we think of a mutant, we think of something that's gone wrong. When we think of that plant has got a mutation, it's all weird, it's nasty. Much like it shows my lack of sci-fi pop culture. The X-Men? No, is Wolverine one of the X-Men? Or am I thinking of Power Rangers? No, Wolverine I think is an X-Men. And so you have mutants can have really cool things. So people have been kind of referring to this in the chat, like what happens if it's quiet? What happens to the last letter? So let's go back to the notebook. I've lost track of my referencing. Was I doing numbers? Was I doing letters? I don't know. Here's a C. Mutation does not equal bad. So you've got good, you've got bad, you've got ugly or neutral. So most mutations are neutral. This is by far and away the most common. As we saw, but looking back at the code, I don't think there's a way of me bringing it up. I can kind of do this. No, I can't do that because then you'll see what else is on my browser. Let's see if this will work. Yes, it will. So as we saw on this, if there was a substitution from, let's see, so remember that leucine had all those different, like there are 6 different ways to code for a leucine. So say it's supposed to be CTT, and then the mutation is CTA. you go from coding for a leucine to coding for a leucine. So although there's been a mutation, no one knows, because no one cares about the DNA. What matters is the protein. So yeah, it's just like, well, cool, I suppose there's a mutation, but no one cares. You can also have mutations in bits of the DNA that don't actually code. So in DNA, you've kind of got a load of stuff happening. Then you've got the bit that codes, and then a load of bit here. I know I've inverted my colours. If you get a mutation here, it's not actually going to change the protein that much, because not all of the DNA is coding. You can also have mutations. So if you're wondering, and maybe you were, why all of this was so colourful, partly because I love colour, but it's because similarly coloured amino acids are similar in terms of their chemistry. So for example, phenylalanine, leucine, isoleucine, methionine, valine, proline, tryptophan and glycine are all non-polar, which means they all don't like water and like fat. Meanwhile, serine, threamine, tyrosine, glutamine, asparagine, yes, it was discovered in asparagus, serine and cysteine are all polar, so they all like to be in water. And so if you change a, I don't know, leucine for an isoleucine, chances are it might not actually make that much difference to the protein. It would be like if I changed this end of the pen, it's not really gonna make a difference, you know? Because it's not on a bit that matters, or if it isn't a bit that matters, it's not changing it in a way that changes the function. So I'm going to go through this quite quickly because I don't want to run too far over on this. But so mutations can be neutral because they just don't affect a bit of the DNA that is the gene. There's lots of structures of the DNA that isn't genes. Sorry, but this is a pause because there is a fox outside my window. Oh my God, did you see that? Did you see that? I've recently moved house and I'm very, very excited about that. Let's go back to the main cam. Well, there we go. That was exciting. Yes, I know there are lots of foxes in London. I don't care. So it can. I have completely lost my train of thought. So it could be that it isn't a bit of the protein that isn't a bit of the DNA that isn't the gene. It could be that it changes the gene, but in a way that doesn't change the amino acid. It could change the amino acid, but that doesn't change the function or the shape. Or it could even change the function or the shape of the protein, but actually that doesn't make any difference. So for example, it doesn't make any difference to me if I have brown hair versus black hair. So either mutation would be fine. So that's why the vast majority of mutations are neutral. Half the time you wouldn't even know you had them. Some of them are bad. A lot of them are bad. Our bodies are well-honed machines, and just as you can't go into, like, I don't know, an iPhone, I don't even use Apple, but if you go into an iPhone and randomly start switching out parts, chances are you're going to break it. Let's be honest, if you don't know what you're doing and you're randomly changing parts around, you're going to break your phone. But very occasionally, you might be randomly switching stuff around and you're like, hey, I don't know what I did just then, but that made it work so much better. Like, you are swapping around all the controls on your... I'm trying to think of an analog example. You are swapping around all of your game settings and you realise that you've managed to unlock this extra feature and you're like, wow, that was cool, unexpected. Most of the time when you mess around with the game settings you'll end up breaking the game, but sometimes you'll get a good mutation. Okay, so if I'm speaking fast, it's because this bit doesn't interest me that much, but you have to know it in order to know the really cool stuff later on. So this is literally just to get you up to the basic level so that we can then chat about the cool stuff. You know, like when your friend's watching a TV program and you're like, oh, I just need you to get to episode 5 so that we can talk about what happened in the thing. This is like me right now. I'm just getting you up to episode 5 of the show, Evolution show. So, not all variation is genetic, and for this I have props. You thought there were plants behind me. That's nowhere near all of my plants. So, these are all orchids, as you can probably tell. These are 2 separate orchids. This is one plant, this is another plant. And you'll notice that they're not exactly the same. So this one has slightly more purple on the leaves than this one. This one, the leaves are slightly longer and thinner than on this one, where they're a little bit squatter. So there is variation between these 2 plants in this pot. However, they are genetically identical, and I know that because they are both cuttings from the same original plant. I made these 2 plants, they are clones. I took a bit of one plant, snipped it off, and stuck it in the pot for it to grow. And because of that, they have the exact same genetic material, they have the same mutations, they should be identical, but obviously they're not. And that's because not all variation comes from your genes. A lot of it also comes from the environment, and a lot of it comes from how the environment interacts with those genes. So you've got, we've got here genetically identical, but there was obviously environmental variation. Maybe this one got a little bit more sunlight than that one. Maybe I remembered to water this one slightly more often when they were in separate pots than when I put them in the same pot. So there is variation despite them being identical. These 2 are both Phalaenopsis orchids. I love Phalaenopsis orchids, they're so easy to grow. And here you can see that while the leaves are very similar, the flowers are obviously different colours. And if I was to take the babies of this one would have white flowers. And if I was to take the babies of this one would have purple flowers. And so it's not like if I took this and grew it in a different environment, it would look like this. These are genetically different. So those mutations we were talking about, this one must have had a mutation at some point in time that caused the flowers to be purple, whereas this one will have had a mutation at some point in time that caused the flowers to be white. And because those mutations are throughout the entire plant, including the reproductive bits, so for plants, that's your seeds and your pollen, or did you know that pollen has sperm cells in it? Like, this blew my mind in first year of university when I heard it. Inside a pollen, like if you were to cut open the pollen, it produces sperm. Like, plants have sperm too. Like, that blew my mind. So inside the sperm and egg cells, if the mutations are there, then they'll be passed on to the next generation. And they're probably not. I'm going to pretend that these are the same species, but with slightly different variation. We would call this intra-specific variation. It gets so confusing because then, put that to one side, if I was to take a different species of orchid, you can see that this is a dendrobium, whereas this is a phalaenopsis. They are different species, so there is inter-specific variation. So specific in this sense means species, and inter, like international. I always literally have to remember it like this, like international competitions are between nations. So inter-specific is between the species, whereas within a species, you never hear intranational. I'm trying to think of a word where you'd ever have intra something. Introspection is within, I suppose. So within the Phalaenopsis, an intra versus inter-specific variation. But there's my orchids. I might as well leave them here for the last little bit. Maybe so you can actually see the flowers. There we go. Even more plants. I'm literally just working with what I have at home, and it's plants. I just fill my house. It will be a jungle. And so you get, briefly go back to the notebook. Did I unplug it? Yes, I did. So we have I'm having to look either side of this plant. We have environmental and genetic variation. So the more mutations you have, the more genetic variation you have. And there's an interplay between the two. Environmental variation. That can't be inherited. We talked about this last week when we were talking about Lamarckism and stuff like that. Stuff that happens to you during your lifetime, unless it affects your DNA, cannot be passed on to the next generation. But genetic variation, can be inherited if it's in the gametes. So that's your sperm and your eggs. Not to scale. Eggs are much bigger than that. So if spontaneously the end of my finger was to mutate and have this amazing superpower that it can now, I don't know, photosynthesize. It can now make food, make sugar from sunlight. That would be amazing. But if it's only in my finger and it doesn't go into the eggs in my ovaries, if I have kids, the genes from my finger will never end up in my kids. Only the genes that go through my eggs will end up in my kids. So if you have a mutation when very, very early on, literally after the sperm and the egg have fused, then you get a mutation that affects the entire embryo, that goes on to affect the entire organism, and that will then get passed on. But it's like a mutation can also cause cancer. Cancer is just a normal cell that's mutated a bit and gone wrong, now can't stop dividing. I say that's all it is. It's terrible, but biologically that's all it is. But cancer in your, the skin, I don't know, the skin on your arm, if you've got skin cancer, that is a mutation in the cells on your arm. but that's not going to get passed on to your kids. And then the final point. Hopefully I can only run 15 minutes behind. That would be good. Mutation and variation is genetic diversity. So the more mutations you have, then the more variation you have, and we call that genetic diversity. And diversity is one of the most important things for evolution. Without diversity, you will not get any evolution. Remember, evolution is the change in gene frequencies over time. So if there is nothing to change, if everything is identical, you can't get any evolution. So on that final point, let's just move that up there. So mutation gives you variation, which gives you genetic diversity. And I mean, you could probably put those two either way around. There's someone at the door. I hope they don't want me to answer the door. Are they going to walk away? I don't know. I'm getting lots of stuff delivered at the moment, so have they walked away? This is very bad. Normally they drop it and run. We'll see. So that is genetic diversity. And I can't actually see what the comments are because I've got a bloody flower next to me. So I don't think it's Mormons. I have been ordering a lot off Amazon. It's probably something for my new pond that I'm going to build and make a video about. So we have genetic diversity. So things that produce diversity. So this is the last bit, I promise. So we have copying errors. Those are the things we were talking about before. Where we went from river to rider, that's a copying error. But also we have, and this is where I'm going to get demonetized, I hope I'm not, we have sex. You or reproduction. And I'm not going to go into this too much, but literally the purpose of sex might well be to create genetic variation. There's still some puzzles as to sex because it's the twofold cost of sex problem. We can go into that later on. But basically, when you have one cell that then splits into two, that then splits into four, that's meiosis. And that creates diversity because it's taking what used to be one long strip of DNA and then let's just do it this way. Oh no, oh no. Oh. It takes one long strand of DNA. It deliberately cuts it up into pieces. Let's not do it like that. There we go, now you'll be able to see it. It takes one long strand of DNA and deliberately cuts it up into pieces. And then, oh, you're being really annoying. You know what I want it to do? There we go. And then it rearranges it. So this is what's happening. when your body is producing sperm or eggs. So now you've got a variation on what was there before. So sex creates diversity, and just because of numbers, large oops. Oh no! How do I go back? Oh, it was doing so well. There we go. Large populations usually have large genetic diversity. Because if you think, each individual is a chance for a mutation to happen, or many mutations to happen. So the more of them you have, the more lottery tickets you buy, the more likely it is that you're going to get a mutation. So you're going to have, so in smaller populations, when there are fewer individuals, there's literally less space for them to go wrong. The more you have, the more chances there are. That, where am I at? 10 minutes past. That's so good, considering it took me like 5 minutes to sort out the audio problems. That is the end of this week's live stream. Next week, same time again, 4 p.m. UTC +1, because the UK is now on daylight savings. And we have, so what is natural selection? I've literally managed to go 2 weeks, so what's that, 2.5 hours, without actually saying what natural selection is, the backbone of evolution. We've done kind of roughly, how did we come to think about evolution? We've done, so what is this genetic diversity stuff? Finally, we'll actually get to talk about about natural selection. I hope you can join me for that. If you can't, then you can catch up afterwards. All of these videos are going to be on my channel, and as a little ask, I am a freelancer in a time when all of my paying jobs required travel in large groups. So they've all been cancelled. So if you do have money right now, a lot of you won't. A lot of you, like me, will be struggling. But if you are in a stable situation, consider I have Patreon and PayPal down in linked below. If not, please just share this stream with anyone you think might enjoy it. Maybe they're in secondary school. Maybe they just want to hang out for an hour on a Thursday afternoon. I hope you have a lovely time. I'm going to go and see if I can chase after that fox, because that's not the first time I've seen it in this garden. I don't know where it lives yet. So thank you very much. Stay safe, and I will see you